what if the recipe for rocky planets doesn't start with water? This week, the James Webb Space Telescope spotted a baby star wrapped in a planet-forming disk that's rich in carbon dioxide and almost missing water, right where Earth-like worlds are supposed to take shape. If true, it bends our models of how planets and maybe atmospheres are born. I'm Your Name, and today we're diving into a fresh Webb discovery from a massive star-forming region 5,550 light-years away called NGC 6357. Astronomers targeted a newborn star named XUE-10, and what they found inside its protoplanetary disk is so strange it could rewrite parts of the planet formation playbook. Using Webb's MIRI instrument, researchers read the disk's chemical barcode. Instead of the usual strong water vapor signal in the warm, inner few astronomical units, the cradle of rocky planets, they saw surprisingly weak water and very strong CO2. That ratio is the head turner. In nearby calmer disks, we see the opposite. Water dominates, not here. Even wilder, the team detected CO2 molecules enriched in heavier isotopes, carbon-13 and oxygen-17-18, tiny fingerprints that can trace the disk's history and processing. Similar isotope weirdness is locked inside some meteorites and comets from our own solar system's childhood. Standard picture: icy pebbles drift inward from the cold outer disk. Cross the snowline, ices vaporize, and boom, water vapor lights up telescopes like a neon sign. That's why inner disks often look water-rich. But in XUE-10, the sign is dim, while CO2 is blazing, and that doesn't fall out of typical disk chemistry or evolution models. So what's different? XUE-10 lives in a hostile neighborhood bathed in intense ultraviolet radiation, thousands of times stronger than around the Sun, thanks to nearby massive stars in NGC 6357. That radiation can reshape chemistry, breaking molecules and reassembling them, potentially boosting CO2 while suppressing water signatures in the planet-forming zone. This result comes from the XUE collaboration, short for Extreme Ultraviolet Environments, a program that targets disks growing up under punishing radiation to see how that environment imprints on future planets. Webb's sensitivity lets them read mid-infrared molecules in the inner few AU for the first time in places like this. Earlier XUE results already hinted that rocky planets can still assemble in harsh UV. XUE-10 adds a new twist. The chemistry could be dramatically different. James Webb Space Telescope, NASA ArcSieve. If a disk's inner gas, the stuff new worlds inhale while they're hot and molten, is CO2-rich and water-poor, you could seed very different early atmospheres. That might influence surface conditions, climate evolution, even habitability paths for rocky planets. It doesn't say no water worlds. Water can still arrive later via ices, comets, or different layers. But it suggests starting conditions vary more than we thought. And those isotope clues? They can tell us where molecules formed and how they were processed, giving a forensic trail from disk chemistry to the fingerprints we see today in meteorites. That's a bridge between their system now and our system's past. Webb's MIRI mirrors, the mid-infrared instrument's medium-resolution spectrograph, covers wavelengths packed with molecular lines. The team modeled the spectrum with slab models under local thermodynamic equilibrium to extract temperatures and abundances. Translation: they fit tons of tiny barcodes to decode what's in the gas and how much. That's how they flagged unusually strong CO2 and barely detectable water in the terrestrial planet zone. Is XUA-10 a one-off, or the tip of an iceberg in harsh clusters? The team plans to expand the sample, more XUE targets, more spectra, to see how common CO2-rich, water-poor inner disks really are. If many extreme UV nurseries look like this, we may need new models for how pebbles drift, how water is trapped or destroyed, and how atmospheres first assemble. The universe is telling us there's more than one way to build a rocky planet. If you want a deeper dive, I've linked the press materials and the team's paper below. Well worth a look. Should we be redefining habitable starting points? Drop your take in the comments. If Webb keeps finding planetary nurseries like this, our textbooks are in for a rewrite. See you next time.